This is the first quiz for 2024 for Dynamics MIU 100. And largely we do try and cover the same sort of material year by year. And so in this particular case, we're covering projectile motion, coordinate transforms, and position, velocity, and acceleration. One thing to be aware of as we're doing all of this is that this only covers chapter 2 of Merriman-Craig. So question 1, a child is throwing a ball and you're given the coordinates at point A where the yellow axes X and Y are placed. The angle that the child throws the ball is 30.5 degrees and it has an initial velocity V naught with the horizontal. Knowing the ball hits a wall at point B, determine the magnitude of the initial velocity and the minimum radius of curvature of the trajectory. So you have a lot of information there. You get the initial height at which the ball is thrown. You have the final height at which it sort of touches the wall and the distance between the thrower and the wall. This is going to cover sections 2.2.2.5 of the text, and it's rectangular coordinates, plane curvilinear motion, NT coordinates, and projectile motion. So in terms of horizontal motion, you know that X is going to be V naught T cos alpha. There's no gravitational, or there's no acceleration in the X direction. Vx then is just the initial velocity V naught cos alpha. You eliminate T right away. You can use that and you can get an expression for X in terms of T. For the vertical motion, you do have the gravitational acceleration. And you'll notice here that what I've done is I've defined it as negative, so I can just use the magnitude. So Vy is V naught sine alpha minus GT, and position Y equals Y naught V naught sine alpha T minus 1/2 GT squared. Rearranging things a little bit with that X term, I end up with this expression, Y naught plus X tan alpha minus gx squared 2 over 2 V naught squared cos squared alpha. You can solve for V naught from that, and all of the terms are given. You have X, you have Y naught, you have alpha, which is the initial angle, X, and Y. So you substitute all the terms in, and once you do that, you have initial height of 0.85, final height of 1.6. You have 20 meters and everything sort of works out. You get an answer of 15.48 meters per second. And again, sections 2.2 and 2.4 in our text. So in the second part of this problem, we're asking you to look for the radius of curvature. And it really is use the definition of a normal acceleration. So AN equals G because in this particular case, the acceleration is G, but it's G at the very top of the curve. If we took any other point, it's just going to be some combination of N and T. But you are asked for the minimum radius of curvature, and I'll actually say it in the next sentence, but that's at the top of the trajectory. And theta is the angle of the trajectory at that point, and it's going to be V squared equal over G cos theta. So the minimum value of rho occurs at the highest point where G cos theta equals G, and V equals Vx, which is the initial velocity V naught cos alpha. Substituting in all the terms, you get V naught squared cos squared alpha over G. Just put the numbers in just below, and you get a rho minimum of 18.13 meters. From that, you're able to get the minimum curvature. So that is that. So in the second question, you're asked to measure a ski jumper's position, velocity, and acceleration immediately before leaving the ramp. Your results are in the table. So you have R dot, R double dot, theta, theta dot, theta double dot. You get numerical values for each. Determine the velocity of the skier immediately before she leaves the jump, the acceleration of the skier at this instant, so still attached to the ramp, and the distance of the jump D, neglecting lift and air resistance, which is a common sort of issue. This is sections 2.2 to 2.4, 2.6. projectile motion, rectangular coordinates, plane linear motion, curvilinear motion, and r theta coordinates. So the velocity of the skier immediately before they leave the jump. So we're doing everything with respect to that measurement device. And so you have an outward radius, which is indicated by the purple line, ER, and a normal to that, or a theta, which is E theta. That's going to occur at 23 degrees with respect to the Cartesian coordinate ij. So as they leap off, or as they're at the end of the ramp, they have a v theta of 9 meters per second and a VR of 30 meters per second, negative as it's pointing inwards. And you determine that from the information you're given. R equals 150 meters, theta equals 23 degrees. All of this information then is put into VR v theta. You use the definition R dot and R theta dot to calculate that. So from this, you get a negative value, minus 30 ER and 9 E theta meters per second. In XY coordinates, you have to do a conversion, of course, and in that conversion, you're going to have cos theta, sine theta for the R component for X direction, or I and J components, and V theta, you'll have an I and J component corresponding to each. You'll notice they sort of flip cos to sine, and sine's also in this. You have to draw the drawing, because if you draw the drawing, you can see where all the motion has occurred. From this, you get the velocity in the I and J direction. These are the same total velocities, V and V, as it is for the R theta coordinate, but it's just different numbers. And if you put everything together, you'll see it's the same. Alpha is going to be given, Vy over Vx is 6.3 degrees, and the magnitude is 31.32 meters per second. So the final velocity before leaving the ramp, 31.32 meters per second at 6.3 degrees below the horizontal. Alpha and V are given here. Sections 2224 to 26. So the acceleration of the skier at this instant, acceleration R, acceleration theta. Again, you're just using the definitions, R double dot minus R theta dot squared, R theta double dot plus twice R dot theta dot. Substitute in, minus 3.54 meters per second squared, 3.9 meters per second squared. Acceleration, hey, it's the same equations. So the R component is cos theta I, sine theta j. Theta component is minus sine theta I, cos theta j. Substitute terms in, minus 4.79 plus 2.21 j meters per second squared. Beta, if you define that as sort of the angle made by that angle, or the angle made by those acceleration terms, minus 24.7 degrees, and the magnitude 5.27 meters per second squared. And that's what it looks like. So again, sections 2224, 26. This was a little bit tricky. The distance of the jump D neglecting lift and air resistance flipping the coordinates. So your velocity you already know, because that's the velocity as you leave. And so you can put in all of the terms x naught dot 31.13 because the skier is leaving the ramp, y naught dot 3.44 meters per second. But the tricky bit here is recognizing once the skier leaves the ramp, they are no longer accelerating on the ramp, but they are in free fall. So they have a gravitational acceleration of 9.81 meters per second, acting down, second squared, acting downward. Substitute in all the terms, put your equations together. At the landing point, you have x equals d cos 30. You can substitute all of that. Y is d sine 30. Substitute all there. Multiply the x by sine, the y equation by cos, and subtract them, and you get 0. And then you can put everything together, put the t's back in, everything works out. You end up with a slightly complex quadratic with t squared t, and there t1 is minus 2.1 seconds, and t2, which is in green, which tells you that's the correct answer. And it also makes sense. It goes forward in time 3.2 seconds. Substituting the final distance, you get 98.65 meters, and D is 113.9 meters. And this is sections 2.2 to 2.4. And it's early in the term. This is usually the end of January when we give this exam. Coordinate transforms are crucial to MIE 100, but it's only a small part of the course, really. We are going to cover a lot more. So, for example, at the time of the quiz, we're about a week or so away from rigid body kinematics and kinetics, which is the second part of the course and a significant part of the midterm and final exam that you will be